Hold on. There we go.
All right, everyone. Thank you for showing up for our talk tonight. We are hosting Natasha Holmes from Cornell University, and she's going to be speaking at our Faces of Physics speaker series. So I want to say a couple thank yous here, definitely for Eli Williamson and AJ Messenger. They have done a fantastic job this semester for reaching out for speakers and organizing this. Eli in particular has spent a lot of time making sure to have everything lined up and organized. So I really appreciate the efforts of the students here to keep this all nice and organized and running smoothly. I also want to thank our physics department here and our College of Science and our university. Of course, they've always been very helpful in working with the students here in the Society of Physics Students and promoting what we do and help us in any way that we can. So I definitely want to thank them as well. Of course, thank our speaker for giving up an hour on her Friday afternoon to educate us. I look forward to the topic of her talk today. I also want to thank the American Institute of Physics. They were the organization that actually helped sort of sponsor this in the beginning. And right now, the speaker series is funded by the West Virginia Space Grant Consortium. So I want to thank them as well. So they've sponsored this now for 2 semesters in a row. So I really appreciate their efforts. A little bit about Marshall here. We are in R2 University. We are going to be in our second round of R2 status. So this will be, I think, year 4. Is that right, starting? But we have 9,000 undergrads, 2,500 grad students. Our physics department is going to be transitioning to a 6-person department, I think, in the future here, with 4 faculty members that are active in research from areas from water filtration to theoretical condensed matter physics. So we have a wide spectrum of research available for students here. If you're interested in our department, check us out at www.marshall.edu/physics, and there is a whole wealth of information on that webpage for you. We have a bachelor's degree with 5 areas of emphasis, so a pure, an applied, a biophysics, a medical physics, and a medical imaging track. So those programs would allow you to get a BS degree in physics, but have a sort of a concentration area that would help you get employment in those types of fields. We also have a master's degree with 2 tracks, a pure physics track where you get a master's degree in physics and then a master's in physical and applied sciences. And we also have a new emphasis in teaching. So a program that works with teachers that are already certified to teach at the K-12 level, and that puts an emphasis on elevating them in their statute to a master's degree with potentially higher pay there as well. So that's our focuses for a BS and a master's degree. So I think with that, if you have any questions for our speaker, don't be afraid to reach out at the end. We will have a live Q&A. And then you can also email me about questions about the department. And I'm sure our speaker would be very happy to receive questions after the talk that way as well. So I think with that, I'm going to turn it over to Eli, and he can properly introduce Dr. Natasha Holmes from Cornell University.
All right. Thank you, Dr. McBride, and thank you to everyone joining our stream tonight. This will be the 12th talk in our Faces of Physics series, and I'm quite excited to hear our speaker tell us about her work in physics education, and I'll be introducing her shortly, but first I have a few quick announcements. So after the presentation, just like all of our other talks, we will have a Q&A session at the end, which will be hosted by MUSPS's Vice President AJ Messenger. We welcome and encourage you to share these questions in the YouTube live chat. If you enjoy this presentation, we hope that you will join us for future talks in the series. Our next talk will be given by Dr. Sheng Sen, Associate Professor at West Virginia University, on March 25th at 7 p.m. Eastern Standard Time. More information about this talk and future talks will be announced soon. If you'd like to receive email updates about upcoming events, we have included information in the YouTube description where you can ask to sign up. While you are down towards that direction, we would also like you to subscribe to our YouTube channel and click the little bell icon to be notified of our future talks and other videos here on our channel. If you wish to watch some of our previous talks, they can all be found here on our YouTube channel. Now it is my pleasure to introduce our speaker, Dr. Natasha Grace Holmes. Natasha G. Holmes is the Ann S. Bowers Assistant Professor in the Department of Physics at Cornell University with the Laboratory of Atomic and Solid State Physics. Professor Holmes received her BSc in Physics from the University of Guelph and her MSc and PhD in Physics at the University of British Columbia. She then went on to do postdoctoral work at Stanford University, working with Professor Carl Wyman. Her research group studies many aspects of student learning, attitudes, and skill development from hands-on laboratory experiences with a focus on critical thinking and experimentation. She also explores issues of equity and diversity in physics and methodological issues and techniques in physics education research. I have not had the pleasure of meeting Dr. Holmes myself, but I found her research online was very intrigued due to my interest and major in physics education. I've watched a talk that she did previously on the University of Manitoba's YouTube channel, which is of a similar topic as today's talk. If you enjoy hearing today's talk, I highly suggest that you check that video out, as well as some of the others that I saw that she has on Cornell University's YouTube channel. Thanks again to all of you for coming out, and thanks to Dr. Holmes for taking the time to talk about her work amidst her busy schedule. And without further ado, Dr. Natasha Grace Holmes.
Thank you so much for that introduction. Let me start sharing my screen. There we go. So I'm thrilled to be here and look forward to having a discussion at the end. My plan is to basically talk until I get cut off. Just kidding. I want to share a little bit about my story about how I got here, and then I'll get through a bunch of research ideas, and we'll see how much we can get through in the time. Little bit about myself. So I was born in Canada. This is me at 1 month old. And you can guess the decade based on the couch. I lived, after being in Canada, I was born in Canada and then moved to the Middle East for a year. So this is me as a 1-year-old in the desert with my sister, my mom, and the camels. We moved back to Canada. I grew up there for a number of years. And I did ballet. It was a huge part of my identity as a child. I think I was about 4 or 5 there. Loved musicals, loved to dress up in costumes. My sister usually dressed me up. And then we moved back to the Middle East, where I finished out sort of the rest of middle school and high school, and then started college. During high school, there was sort of an interesting transition period when I went from kind of an average student to a hardcore science student. And this is my dog who likes to make an entrance while I'm in meetings. Sorry about that. And so I started getting awards for, I started joining math competitions and doing awards for things, and sort of decided that I wanted to be a scientist, mostly because of forensic science. I liked the idea of CSI. And sorry, he will leave in a second. And I started doing outreach with kids as well to sort of share this passion for science with others. And at the time, I was unsure what I wanted to do. I was getting really excited about my physics and math classes, especially, but this idea of forensic science was still really intriguing to me, but it turns out I wasn't really enjoying my biology or chemistry courses. And my first year physics professor, I went to him to ask sort of some advice, and he went through a bunch of careers that you could do with a physics degree, and none of them interested me. But he said, whatever you decide, you're going to do it for a long time and spend a lot of time doing it, so you'd better love it. And so with that, I switched my major to physics and sort of have never looked back since. I think what started to intrigue me about physics was the beauty of it. I think I really liked the idea that the world could get explained through mathematics. I thought that was elegant and rational. I also really liked the idea of being a theorist, where I could just go to a coffee shop and do physics and think about physics and solve deep problems of the universe from there. And so I started doing some research experiences as an undergraduate. My first one was working on the alpha particle X-ray spectrometer, this thing, which exists on the Mars exploration rovers and the Mars Science Lab, the previous generations of rovers. And I worked on some calibration where we were looking, it was almost geophysics and particle physics kind of merged, where we were sort of calibrating this detector to understand how it looked at different types of rocks. So I thought astronomy was maybe my thing. So the next summer I did a theoretical planetary astronomy research project. where we were simulating solar system formations and making really cool, pretty pictures like this. Turns out I really like astronomy, but I don't love just sitting at a computer and analyzing data. We'll come back to that. But I got my undergraduate at the University of Guelph in physics, and then moved on to graduate school at the University of British Columbia. And at this point, I decided that particle physics was my thing. So I started on a neutrino physics project called T to K, where we were looking at neutrino oscillations. And through all of this, I think I was generally captivated by just sort of so many beautiful things about physics. But I started to learn that it was sort of much, much more than the relationship between math and sort of the universe. And I started seeing a lot more complexity to the field. And I think I sort of had this vision in my head of this sort of lone genius physicist mentality. And that really started to change at the beginning of grad school. And it became clear to me that I loved so many different aspects of physics and not necessarily one in particular. Ultimately, I really loved learning physics and I loved things to do with school. I started TAing as a graduate student and then took a teaching and learning in physics course and learned about the field of physics education research. And that just sparked so many things in my, so many interests and so many ideas. And so I started looking into whether I could do that for my PhD. And I found an advisor who was willing to take me on. He was sort of transitioning into physics education research at the time. And he said, you can come and work with me, but you have to study labs. And this was sort of the thing that he was interested in. And so this is an important statement because I found when I was an undergraduate, a Facebook post that I made at one point that says, not happy with physics labs. And I think that this post is very meaningful in retrospect many years later. That at the time, so my reaction when my advisor said, you have to study labs was, but I hated my physics labs as an undergraduate. I don't think I should be studying labs. To which I said, I eventually flipped it around. I hated my labs as an undergraduate. I'm the perfect person to study this and to try to figure out why it was so awful for me. So this is what I do now. I study introductory physics labs and have even moved into some upper division stuff, even some other disciplines, but have been trying to understand how we can do better with our undergraduate physics labs. So this was my advisor, Doug Bond. I got my PhD in studying introductory physics labs, moved on to Stanford to work with a wonderful group of folks there doing science education research broadly. And then started at Cornell, where I've been developing my own research group here. So this is some of my team a couple of years ago at a Cornell hockey game when Cornell was actually playing the University of Guelph, which was very exciting for me. Cornell creamed Guelph. It was embarrassing, but that's okay. And then, of course, we've been sort of surviving through the pandemic. So this was us at Halloween last year, I think, celebrating all of dealing with our new formats. So my goals now as a physics education researcher are ultimately to figure out how we can help students authentically engage with physics early on, and particularly experimental physics. And then as was mentioned, I also have an interest in issues of equity, diversity, and inclusion. So helping women and students from backgrounds historically underrepresented in physics feel welcome, encouraged, and excited by physics. And again, I think that there's an opportunity with the labs to do that. And so in general, I think there's sort of, my story helps demonstrate some of the ways that I think a lot of people, physics is not what a lot of people think it is. And it certainly isn't what I thought it was when I first considered majoring in physics. And I think that this also connects to some of the representation issues that we have in the field. So this is a picture from the Atlas celebration after the Higgs was discovered, right? This huge, this isn't even a fraction of the folks involved in this in the LHC. Thousands of people working together on this shared mission really is the opposite of the sort of lone genius mentality that I think often gets shared. And in addition to collaborating, physicists do things like write. And I remember in high school English deciding that I was never going to take an English class again unless it was required, and I would never have to write again. And that's why I was going into science. So I would just do math all the time. Turns out 90% of my job now is reading and writing. Go figure. We also get to be sort of visually, visual artists. So we have to make figures that represent lots of deep information, and we have to try to make them both communicate a message, but also be kind of visually appealing. And so that's an interesting challenge that I wasn't expecting. And we have to be creative, and we have to be ideas people and think outside the box, and try to come up with new perspectives and new methods and new ways of looking at the world. And it turns out we also have to be like kind of entrepreneurs and business people. We have to write grants and convince people to give us money to do stuff, which I wasn't expecting to do. And we get to be educators and teachers. And I get to have a lot of fun doing demos and things like that with students. So I get to be a performer almost. And we give talks like I'm doing right now. And I've been on media venues and all kinds of different stuff. So it's really a very different job than the one I was expecting to be a physicist. And then of course there's application things. Physicists also, it's not just about fundamental physics. We also do things that will help the world, like create the internet, radioisotopes for health, connecting to things like semiconductors and technology, superconductors, quantum computers, all that fun stuff. Okay. And so I'm really convinced that by sort of better showing this broad range of what physics can be, we can get people really excited about physics in new ways. We can get different kinds of people excited about physics. And I think being a little bit more authentic to what the field can really look like, what it means to do physics, I think is a big part of sort of what I've been focusing on. So this is the group that I am currently working with, the folks in my research lab. We've got a wonderful group of postdocs and graduate students and undergraduate students, including some collaborators in biology education research now, as well as a couple other disciplines here at Cornell, which has been very fun to grow this community here. Okay, so that's my very big picture journey into physics. And I hope during the Q&A we can have some conversation about that a little bit. I'm going to talk for the next little while about this first piece, sort of what does it mean to help students engage authentically with physics, especially with their experimental physics early on. And so mostly focusing at the undergraduate level. Okay, so the title of this talk, I think, is The Trouble with Traditional Physics Labs. And the punchline is, I don't think it's what you think it is. And it certainly wasn't what I thought it was when I first started this research. So I have a dabble in social media and Twitter with work, but in the past I have asked people to complete the sentence, my intro physics labs were blah. And if you follow me on Twitter, you're welcome to go and share that with me now, because I like to get new ideas. But let me, in the interest of time, show a word cloud of what I got the last time I asked this question on Twitter. This is what people said. So the size of the word represents how many people said it. And big and bold right in the middle is that they were forgettable. There's a lot of other stuff in here, non-existent. Some people don't have them. Where is it? Tedious, pretty tedious comes up down here. And then, predetermined outcome, some people feeling that they were useful, a bunch of getting stuck, that's always good. Lots of different stuff in here about people's sort of experiences with these intro labs. And forgettable obviously is a problem, right? Because if you're forgetting something, it probably means you didn't learn anything. But beyond that, we get all kinds of emotion. I think a lot of people have emotional responses to labs, and my Facebook post is one example of that. We once gave someone a series of surveys to students on paper about a bunch of sort of data analysis questions. And one of the students just decided they were done answering our survey and told us this: I hate labs, theoretical only. Very emotional response to my survey. Like, they're just done answering this thing. And so I think, this sort of sets up this issue where it's possible students aren't really learning anything, and they're having some pretty strong negative reactions to what's going on. And so this is what we're sort of trying to disentangle. So when I talk about traditional labs, these things that are forgettable and frustrating, the traditional labs are typically ones that are aiming to use experiments in a hands-on way for students to demonstrate or observe some sort of physical phenomenon. And as a result of that aim, they're highly structured and confirmatory. So let me go through some examples of what this might look like. Thinking about the highly structured first. So this is a set of instructions from what I would consider to be a very traditional Atwood's machine lab that really walks students through what they have to do in the experiment. So if I zoom in on some pieces, so we're using pulleys, we're building an Atwood's machine. They're told to drop the larger mass through distance, use a stopwatch, set up a spreadsheet, drop the mass 3 times, do it for 7 different mass pairs, put this on the y-axis, this on the x-axis, et cetera, et cetera. So all of the decisions that you would have to make in carrying out this experiment are made for the students in advance. The instructor has laid out, this is exactly what you need to do. No need to make any decisions yourself, just follow these instructions. And then the second piece is that they're confirmatory. So in the Atwood's machine lab, right, they're told at the end that the slope should be acceleration due to gravity and the intercept should be close to 0. They're told exactly what answer they're supposed to get from the experiment before they've even done the experiment. And this is necessary when the goal is to demonstrate or verify a physics phenomenon, right? You want the students to get that outcome because otherwise they're not going to learn it, they're going to get confused, whatever it may be. So when I first started as a physics education researcher and my advisor said, you have to study labs, my instinct was the problem has got to be with the structure. I really thought that was the piece that was the issue, that students could go through this experiment without sort of turning their brains on, right? You didn't have to actually think for yourself as you were going through those experiments. What we've learned from our research, to give you the punchline at the beginning, is that the confirmatory nature may actually be the bigger problem. And I will sort of unpack a little bit about what that means. So before we get there though, big idea number one, the biggest issue about why this is important at all is that our data are saying that traditional labs are not actually supporting students' learning of these physics concepts that they aim to demonstrate. So this is their number one goal, and the research that we've been doing is saying they're not actually doing that. So we did a study number of years ago where we tried to ask the question, does taking a lab that's intentionally designed to reinforce sort of theoretical physics material, does it improve students' understanding of that material? And we took advantage of a few institutions that had optional labs. They were designed with this aim in mind, but they were optional, sort of like supplement to the lecture material, a way to sort of reinforce the things from lecture, but not everyone had to do it. And so because they're optional, we've got a sort of controlled experiment set up where we've got a group of students who take the lab, a group of students who don't take the lab, and everybody takes the lecture. And so because the goal is to improve their understanding of the course material, we use the final exam as sort of a measure of their performance to compare these two groups. Now, there's obviously, when a course is optional, there's sort of some selection effects, some biases essentially, in who's going to opt into taking the lab or not. And so we found some ways to sort of control for that in the analysis, partly taking advantage of the fact that not every exam question has an associated lab that reinforced it. So you can sort of use the non-lab questions to normalize the student's performance. I'm not going to go into the details, but you can grill me on it if you don't believe my data. But through that normalization, we were able to calculate what's called an average lab benefit. So it looks at sort of the how much, so positive would mean that the lab over and above what's happening in lecture improves students' performance. Negative means the lab hurts it, and 0 means there's no difference between these two groups. So you can sort of think to yourself, what would you expect? So is it going to be that this average lab benefit is much, much greater than 0? So it's a very large effect to taking on the lab on students' conceptual physics understanding. Maybe it's just a little bit greater than 0, so a small benefit. Approximately 0, there's no benefit. Less than 0, actually the lab hurts their learning, or maybe there's something, it depends on the course of the institution. We did this at 3 institutions, 3 courses at each institution, so there may be some variability there. Okay, So thinking to yourself what you might expect, this is what the data show. So we've got each of the average lab benefit for each of the courses with their error bars, and within experimental errors, they are not different from 0. So across the board, there's no effect to taking the lab on students' exam performance, again, controlling for those selection effects. So we say that this provided a sort of, there's no, we can't possibly say that labs can't ever improve their performance. But what we've shown is that as they are currently designed, we can't measure it. So it's a measurable, there's no measurable added value, I think was the language we like to use, to taking the lab on students' exam performance. So that's not great, because this is exactly what they are designed to do, and we can't actually find a better fit of that. So then we have to go through and try to figure out what's going on and what do we do about it. Because the other sort of big piece of labs is that if they're not teaching conceptual physics, they should also be teaching sort of what it means to do physics, what experimental physics actually is. So the big idea number 2, why confirmation I'm arguing is actually the bigger issue, is that confirmation conflicts with the goal of teaching authentic experimentation. You want students to understand what it means to do experimental physics. Having the outcome predetermined is just fundamentally not going to work. So how do we know that? So in our labs for a number of years, we've started our intro physics labs with an experiment where students test the angle dependence of the period of a pendulum. So we have them measure the period at 10 and 20 degrees, compare them to see if they're distinguishable. Are these periods different? Students have seen the equation in class. Often they've derived it, which is a key detail, that shows that the period only depends on the length of the pendulum and some fundamental constants. So the mass doesn't matter, the angle doesn't matter, etc. The derivation, of course, at some point you make a small angle approximation. And that small angle approximation means that the difference between the period when released from 10 and 20 degrees for a typical sort of in-lab pendulum is going to be about 0.02 seconds. So you need approximately 0.01 second precision to be able to measure that difference. And if your sort of reaction time uncertainty on a stopwatch is 0.1 seconds, if you let that pendulum swing 10 times, then you can get your uncertainty down to 0.01 seconds. So this is totally measurable in a lab. And yet, every time we run this experiment, fewer than 10% of the groups will actually measure this, detect this themselves in our labs, even when we have explicit instructions for the students to find ways to reduce their uncertainty as small as possible. We've done this at several institutions now. So why is this happening? Here's conclusions written in the lab notebooks by a group who did actually pick out the angle dependence, and they go through this wonderful conclusion about the small angle approximation and how that really depends on the precision of their measurement, right? That if you can make a precise enough measurement, you can show that theoretical derivation is just a good approximation and reality is slightly more complicated. This is beautiful. But there's something very important about this, and that's right at the top. They say the opposite of the expected happened. So even though they knew they'd seen the small angle approximation, this was available to them, they really did not expect the periods to be different. And what we found is that this expectation is really important in how students engage with lab. So a student at the end of the year in an interview told me, the pendulum experiment we did at the beginning of the year, I think that really made a mark on me because I went in there expecting the period at 10 and 20 degrees to be the same because that's what I was taught. And then when you finally figure out that, oh, it's supposed to be different, and then I was like, oh, I probably shouldn't be doing experiments with bias going in. So we started looking into this bias that the student sort of flagged. And so I'm going to tell you a quick story of 2 students, Ali and Ben. So Ali and Ben are doing this pendulum lab, and they start the lab explicitly saying to each other that the purpose of the lab is to verify the model, to show that the angle doesn't matter. So one of them says, I was thinking we should do 2 different angles just because I was kind of writing the pre-lab up with the sense that the purpose of the lab was to prove that the period is not affected by the angle. And this expectation ends up restricting sort of the way that they engage with the experiment. In particular, they are reluctant to seek any evidence to refute their expectation. So one of them says, do you think it's worth doing a third degree, like a third angle, so 10, 20, and something higher? And the student says, no, they're just going to be the same. So there's no point in doing another one because it's just going to be the same. But of course, we know if they'd gone to a higher angle, the difference would have been bigger. They may have actually seen it. Even when an instructor goes in to try to sort of push them along in the direction, they basically ignore the instructor. The video of this is pretty hilarious. So the instructor comes over, says, this is a theoretical equation. Are there any things that could make the two angles, the period at the two angles distinguishable? And the student says, I think maybe the angle of view, which to me, this is sort of a human error throwaway. Unclear how it would cause 10 and 20 to have different periods, but anyway. Another student comes over to check in on how their experiment is going. They ask, how's your T prime value? This is a sort of analytic tool that we give students for comparing two measurements. So it's the difference between the two measurements divided by their combined uncertainty. So it's like saying a 1 sigma, 2 sigma, 5 sigma difference between these values. So how's your T prime value? So they're expecting that this should be small, but they've gotten to a point where now their T prime value is starting to get quite big. And the student says, it's kind of a pain in the butt. Ours was great, but the instructor was like, why don't you try something to make it even better? So we started making it better and it just gets worse. So as their uncertainty is getting smaller, this T prime value is getting bigger. They're starting to see the difference between these two angles. The instructor is pretty frustrated about this. So am I. And then ultimately they engage in what we call a questionable research practice, not necessarily unethical, just questionable. So the students had found this great way to reduce uncertainty by letting it swing more times. And as the uncertainty got smaller, this T prime value got bigger, the periods looked more and more distinguishable. So they make the decision to go back to single swings with the higher uncertainty. So the student says, we'll see if a greater range, greater uncertainty will help or hurt our data. Ooh, I like the T prime. The standard deviations are like an order of magnitude higher. So they are now excited that they have a bigger uncertainty and the T prime is small and the equation makes sense again. And so we've seen this sort of behavior in a lot of different ways, not just in how students engage, but even in the way that they write their lab reports, which they then submit to get graded. So from the lab notes, we've seen things like, we'll now try to be more precise by recording 10 consecutive periods so that the periods are more alike. So an explicit aim to confirm. Or based on our results, our values are possibly different. However, considering the unreasonably low uncertainty, it is believed that our values were probably not different. So we tried using 0.2 seconds as our uncertainty. And after doing so, our T prime is 0.8367, which would prove that our values were probably not different. This is the classic, my value for G doesn't agree with any error bars, so let me just make those error bars bigger. Look, now it agrees, we're good. And we've seen this sort of questionable research practices when we've run this experiment. Anywhere between 10 and 60% of the student groups will exhibit one or more questionable research practices during this pendulum lab. And so in another interview, a student really helped articulate what's going on here. So they say, when you realize that there's something wrong with your experiment, if you're just trying to get the result right there and then, well, you get frustrated because it's not working. And then sometimes when you don't get the results you want, you're tempted because you know exactly what result you want. So it's tempting to just massage what you've gotten until it looks like something like a distant relative of what you want. Okay. And so to me, the moral of this story is that this goal that we have in the labs for students to obtain a particular answer, to verify or confirm the textbook theory or demonstrate it, can lead students to make some questionable decisions during their lab. And this confirmatory goal conflicts with the goal that we have to engage students in authentic experimentation or authentic science. If we want students to understand what it means to do science and to do experiments, then having the answer at the beginning is fundamentally not going to do that. And we think that this moves beyond labs. So there's some really nice survey research who have shown that when you ask students sort of what the purpose of experiment is, many of them will say that it's to confirm previously known results, and that experimental results should be evaluated based on how well they agree with theory or with previous results, as opposed to sort of evaluating every result on its own. And so there's an important sort of tension here where the goals to use lab to teach conceptual learning really conflict with the goals to teach authentic physics. Okay. So the third piece of this is going back to the idea of the structure. And big idea number 3 is that structure is actually not inherently bad. And there's tons of ways to demonstrate that by having more structure in a class, it significantly improves learning in a lot of ways. So I'm just looking at the time. I think I can get through this. So we did a study where we did sort of a control group, which would be a traditional lab, and what I call an intervention group, which was a restructured, the same course restructured, specifically to teach critical thinking skills, experimentation skills, and both of the classes wanted to teach some uncertainty and data analysis skills as well. So the Atwood's machine lab that I showed at the beginning was taken from this study. So this is one of the traditional labs in that study. And so we took the instructions for this and just restructured. So this is what the restructuring looks like, and I'll zoom in on some pieces. So now, rather than telling them to do this for 3 mass pairs and repeat for 8 trials or whatever it was, we asked them things like, what are going to be some sources of uncertainty? What might you do to reduce this? You're going to do this for a couple different masses. How many do you think you should use and why? Et cetera, et cetera. We get them to sort of iterate. We do a pilot experiment, refine their designs, talk to some other groups, et cetera, et cetera. And so part of this is sort of we've taken statements and turned them into questions, and also sort of added a bigger sort of community. Go and look at what people are doing around the room. This isn't a one and done. You can try a couple different things and see how things work, more like what an experimentalist would actually be doing. And so what we wanted to look for in the instructions, first of all, is just a better sense of what this structure looks like. So we had some intention, some ideas. So then we went just to look at how well did we actually sort of execute this. So we looked for 12 what we called sort of productive decisions about planning an experiment, executing an experiment, and reflecting on it as you go or at the end. And so we first of all just went through the 2 sets of lab instructions to look for evidence of whether we sort of cued these instructions or specifically, or gave them sort of the decision to do, or gave them sort of a prompt. So again, this is sort of the difference between take 3 trials versus how many trials are you going to take. And so when we look at the control group and the sort of what this structure looks like, we see that when it comes to planning the experiment, most of the sort of decisions are made for students in advance. So for the most part, the dark gray is that the decision was made for them. They didn't really have an opportunity to make it. Light gray is something that's cued, like a question. So for the most part, lots of structure there, but very little structure for executing and reflecting the experiment. So it's sort of like plan it, do it, and then you're done. In our intervention labs, there's a very different structure. So first of all, if you just add up how many of these 12 decisions are either cued or given by in each of the labs, there's actually more structure in the intervention, right? We are prompting them about more multiple things. Only one of the decisions is actually made for them. The rest of them are all cued. And the structure is very different from the control group and also variable every week. So there's a little bit of sort of different things are coming and going. And then we tried to really sort of pull the structure out at the end to let them be a little bit more independent. And as a result, when we look at how many of these different decisions do students document in their own lab notes, for the intervention group, there's basically none. And we'll just ignore the color for now. So very few decisions made by the control students, less than one of the 12, on average, less than one of the 12 decisions are documented in their lab notes each week, which is, for the intervention, however, we see a very different picture. So the students are recording way more of these decisions. there's fewer decisions documented in their notes than there were in the instructions. So it's interesting that they're really not actually just following our instructions. There's a little bit more independence there, maybe in a bad way, but that's okay. And then there's some interesting patterns sort of over the weeks. It's not a ton of data to make sense of it, but we think that there might be something that sort of the first week, they're not used to this new structure and they're not quite sure what to do, but they kind of figure it out by week 2. And we do think that there's some variability. These 2 labs are what we called confirmation labs. So basically they were supposed to measure gravity. They knew what the answer was. So we have this sort of hypothesis that when students are asked to confirm, they aren't doing sort of as much independent decision making, but that's very tentative at this point. Okay. And then the last piece is that we also had them, we also looked in a couple of the experiments whether they make good decisions. So first we looked at whether they explore their results. Thank you. So so they get a result and not explore it means they just get the answer and then they write it up. The dark blue is going to be that they got their result. It came out as they would expect based on theory, and they still went and explored it. And then the lighter blue is that they got a result that was ambiguous or conflicted with their expectations. And so they went and explored that. And so what we see sort of understandably for the control group, they're just not exploring their results at all. So over 97% of the students or so get their result and they're done. In the intervention group, in contrast, we see 40% of the students explore the results that come out conflicting or ambiguous. 20% go and explore results that actually came out as they would have expected. And then there's still some work to do with sort of 40% of the students up here. And then the last thing we looked at was sort of the quality of their conclusions. So do they actually provide a conclusion for their experiment? If they do, does it contradict their data or is it supported by their data? And so here we have 40-ish% of students in the control group provide conclusions that are supported by their data, but over 50% of them provide conclusions that actually are contradicted by their data. And typically in these cases, they agree with the theory, but their results actually disagree with sort of the textbook idea. And that number shrinks a ton in our intervention, which is pretty exciting. So this is, some good evidence of critical thinking going on here. Okay, so big idea number 3, structure is not inherently bad. In this study, we actually basically added structure to the labs, but we really restructured it. So these statements like take 10 trials were converted to questions. How many trials are you going to take and why? And then we also added structure for executing and reflecting the experiment. So once they've done the experiment, they found, they did 5 trials. Was that enough? And give them the opportunity to sort of iterate on it. And as a result, students in the intervention lab made more and better decisions about their experiments. Okay, so I mentioned at the beginning that I'm from Canada, so I'm going to jump into a very Canadian analogy. And this is that if I was trying to teach a student how to play hockey, I would never just throw them into the NHL. But I also wouldn't only ever have them, I wouldn't just show them what to do, have them do it, and then consider it done. What we do when we're trying to teach someone to play hockey, you first start by teaching them how to skate. And even then, you start by holding their hands or you give them the little chair things. And you do a bunch of drills and exercises and practice, you learn how to skate backwards and then you practice skating forward and all of these sort of pieces. The other piece that I think is important to learning how to play hockey is that every practice, you're going to have, a game where the kids get to play against each other for fun to see what it feels like to really do the thing. So if it was just drills all the time, that wouldn't be fun either. So you want to make sure that they get to play the game every once in a while. Okay, that's my hockey analogy, which we've sort of put on a set of axes. If you think about the structure on one axis and this like confirmation versus discovery on another axis, our traditional labs are up here in this top corner, highly confirmatory and highly structured. There's my dog again. And then down in this corner is what I call the anything goes labs. So this is just like, here's an empty room. Go do, ask your own question and do what you want. We're not advocating for going here necessarily, and certainly not right away. Instead, we want to start up in this high structure, but probably avoid the confirmation as much as possible. You want to give students time to play down here, but there's going to be some kind of zigzaggy path over time that sort of gets them down to the bottom. And we're still sort of trying to study what that path actually should look like. Should you, start up here and jump down there? Should it actually be more like a sine wave? I don't really know. We're still trying to figure that out. But we know that this is bad. We know that this on its own is probably bad. But there's lots of space in between those. So in terms of things that we're doing now, there's a lot of research questions that we're playing with. So one of the things is, again, the students have this expectation that lab is this place to confirm. So how do we help students with this sort of reframing of lab? What is the optimal wiggly path from high structure to low structure over time? Open-ended labs can be really overwhelming. So how do we sort of build confidence and creativity and support students through that? There's a big question of just the group work aspect to labs. How are teams sort of navigating the open-endedness with each other? What kind of group work dynamics are at play there? And then as new TAs and instructors are taking this on, how do we sort of support them in implementing these ideas? My son is going down for a nap, if you can hear him. And with that, I will thank all the wonderful folks we've been working with, and I look forward to our Q&A. Thank you.
Thank you very much.
Yeah, thank you, Dr. Holmes. That was a great talk. I know this might be a little biased because I was the one that picked this speaker, but I think this was my favorite so far. But yeah, I'm going to go ahead and give it over to AJ. I see my wife was in the chat. So AJ, I hope you ignore those comments. But yeah, AJ, if you want to go ahead and start us off with our questions here. I see 2 from my wife that she put in there.
Yep, I'll go ahead and start with the questions. Again, thank you, Dr. Holmes, for your talk. I enjoyed it, and I'm sure everyone else that was watching enjoyed it. So let's start off with a question from Julia. What is something you would advise future teachers to do better whenever trying to teach physics?
Yeah, that's a really great question. And I think there's a lot of ways to think about that. I've focused on labs, but labs is only one part of what physics teaching looks like. So I think one of the things that we've really focused on is this role of confirmation. I think trying as much as possible to give students these opportunities to ask their own questions, design their own experiments, and using lab time, using as much of physics class, I think, as an opportunity for students to do physics. And I think focusing on the process rather than focusing on the product of what physicists have learned about the universe. And I know that's much, much easier said than done, but I think there's sort of a nice reframing there of focusing on the process over the product.
Gotcha. She also had another question. Did you ever have a physics or science inspiration growing up that further motivated you to study your field? All good.
That's a great question, and a really, I think, interesting one. As I said, my background as a kid, I was into ballet and music and theater and things like that. My sister was really the sciencey one. She ended up being a chemical engineer. And so I think as a kid growing up, science was not really my thing. But certainly once I got to college, well, I guess once I got to high school, my science teachers were so influential. Yeah, all of my science teachers were so influential in just, showing me that I could do physics. I think that was a really big part of it. And then once I sort of got to college, a number of instructors who really sort of helped motivate me and keep me going. Professor McFarlane, as I already flagged out from my first year mechanics class. So I think that was sort of an interesting, I think a lot of people talk about, when they were a kid, they were inspired by, my sister was certainly inspired by Carl Sagan and lots of other people. And I guess we watched Bill Nye the Science Guy as kids a lot, but I would have watched whatever my sister watched. So that just sort of, so I think I'm sometimes non-traditional the way that a lot of people who were really into this since they were really young. For me, I really found science later. And it really just sort of became something that I was good at and enjoyed doing myself. So.
Awesome. Julia also wrote that this was her favorite 100%. And Faith said that the little costume when you dressed up was cute. So they enjoyed that. They enjoyed that portion. I have some questions myself, if you don't mind. Have you been able to test any of your findings yet in order to try and jump from the traditional lab all the way kind of to the anything goes, not exactly an anything goes, but have you been able to test any of your, let's say, hypotheses yet?
Yeah, so we've done a couple of things here at Cornell. So we did a controlled study where we revamped the courses here and compared sort of a number of student outcomes to the traditional system. I think that what we haven't done and what we need to start doing is comparing the different forms of what I call non-traditional labs, right? So finding a bunch of different combinations of these other variables, and instead of always just comparing to the traditional lab, which we kind of know is not great, start doing the pairwise comparisons on the other side and figuring out which of these pairs is actually better. We have tried an anything goes lab. So now the second lab in our sequence is an open project course where the students have a whole semester to do one project where they, in groups, they choose a research question and then carry out the experiment throughout the semester. But even that we've added a ton of structure to. So the students actually have to write a proposal that includes some pilot like preliminary data. It gets peer reviewed. So everyone reviews each other's proposals. It goes out to an external evaluator who's another faculty member in the department, and they get feedback from them. And then they've got the rest of the semester to actually carry it out. And they, even then, right, they're sending weekly reports to the TA and the instructor and a bunch of other stuff. So I'm still not ready to just like totally they're in charge. I don't think anyone, I mean, even at this point, right, I don't get to do whatever I want. I still have to, you know, get funding from the NSF and various places, right? So you're always at the whims of peers and experts. So I think we've sort of set that structure, those constraints, and trying to emulate that process a little bit.
Gotcha.
Yeah, I have a question here. So with the flat line of the zero added benefit, was any differences in how the three schools, I know the 2-hour time frame for a typical lab that we have, I mean, that's really important to instill, you know, what you want to get accomplished with the students in that time frame, especially for the traditional labs because they're highly structured and trying to get everything done. But was there any differences in how those three institutions required students to report their results? Like, did some have differences in the structure of lab reports? Did some not do lab reports? Were some, you know, what were the differences there? And did you, that's sort of question one, and question two would be, was there any differences with those three schools or other schools where they have lab exams versus ones that don't?
Good question. So I'm trying to think back. As far as I can remember, all three of the institutions had like worksheets that students filled out for each of the labs. So rather than a lab report, it was like questions and answers, almost like a tutorial that they would sort of fill out for those. So no differences on that one, but all on the, so we don't really know what the lab report does, but there are people who are studying the lab report, and that's a whole other thing. The lab exam is an interesting one, and I don't remember if any of these courses used lab exams. I know that at least one of them didn't, but I don't remember what the other two institutions did. And so that's an interesting piece, right? Is that if you have a lab exam where at the end of the semester, the students know that they're going to have to be able to, you know, reproduce an experiment or do a new experiment, that sort of sets up a very different set of stakes, I think, which then means a different way of sort of engaging with the lab while they're doing it. So that's an interesting, we haven't looked at that, and I don't know anyone who's looked at that.
Okay. Thank you.
No problem. That's if you're looking for something to do. It's a study worth doing, right? What is the role of the lab exam in student experience?
Yeah, I mean, that's a question that I have because you know, we have 2 lab exams for our students here, And, I think there's mixed responses on that. So I was kind of seeing, you had the data there that was kind of flatlined across. I was wondering if maybe 2 versus 1 or something like that, if there was a difference there, if all 3 of them were the same. So.
Yeah, it's a great question.
I have some questions here myself, as I mentioned to you before we started here. So one of the things that I was kind of thinking of when it came to physics education research, I've read a few papers on this, and I know a lot of times there has been resistance from the instructors whenever it comes to being told, okay, what you're doing isn't working. Let's try to fix things. So what are some roadblocks that have come up in your research that you've seen?
So many. So many. And it goes back to when I first started this research. I think I had I was finishing up my master's degree where we were looking at just student understanding of data analysis, and sort of the use of computer tutors was actually what my undergrad or my master's was focused on. And I was considering the transition to really study labs, like just sort of study what's happening in labs. And I was actually advised by someone, Sarah Gilbert, who was at the University of British Columbia at the time. Her response was, don't study labs. Everyone has their own sort of personal stake in labs. It's an institution that you just can't contend with. Don't study labs. And I responded with, challenge accepted. And I think that's true, right? Every institution has, every department, every individual lab instructor has their own sort of philosophy for labs. And a lot of the time, like, they've built the equipment with their hands, right? So they've got a lot at stake, a lot invested in the structure of these labs. And unfortunately, that variability also means it's been really hard to study because everyone's doing it so slightly differently. And so, making comparisons at multiple institutions becomes really hard. So that's one of the pieces that we've tried to sort of grapple with is, can we take advantage of that variability to look for some kind of constancy across these different labs? But yeah, as you say, we've certainly ruffled some feathers, I think, with some of the claims that we've put out, but it has sparked a lot of discussion and conversation, which sort of forces people, if they're going to argue for the strengths of their labs, then they've got to show us the data, right? That it sort of forces people to be more systematic with what they're doing by sort of presenting some evidence that disagrees with the norm. So it's been, I've, if I can say, live on the internet, I've enjoyed sort of ruffling feathers because it really does spark that conversation. And for me, that makes for better research from all of us when we're in a debate. If we're all just agreeing with each other and moving things forward, then you're just not going to get the same quality of critical thinking, I think, as when you all kind of disagree with each other in a very healthy, constructive, and collegial way, of course. But
yeah, thank you for the answer. That was actually really enlightening. So another question for me, this is more of a thing to benefit me, but I think people would benefit in the live stream from knowing, in case there's somebody watching that's kind of wanting advice on this. So if someone were to pursue an education or a career in education research, what would be some of the steps that you would recommend taking? Like, say my situation, I'm about to finish my undergrad. What would you recommend me doing to kind of get into that?
yeah, I think more and more there's starting to be a lot of opportunities for engaging in research, both as an undergraduate and then as a graduate student. So there are a ton of REU, so the NSF runs REU programs, research experience for undergraduates, and there's a number of institutions that have physics education research specific programs. So getting involved in things like that to really see what it means to do the research. So one of the things that I mentioned at the beginning that I forgot to pick up was that a lot of the time we go into physics education because we love teaching and we love learning. And I said I avoided planetary theoretical astronomy because I didn't want to just sit at a computer and analyze data. Turns out most of what I did for my PhD was sat at a computer and analyze data. And so I think having that experience, really knowing what it means to do the research, it's not teaching. It is also, it has the implications for teaching, but ultimately what we're doing is looking at data. And so, making sure that that's a place that's exciting. And then the other piece is that there's so many different ways of doing physics education research, from very, quantitative, big data stats methods, and we're people now exploring machine learning applications to PER, all the way down to very qualitative case studies, interviewing students, observing them in the classroom, and everything in between that, right? And so getting a nice flavor for all of the different flavors of, getting a taste for all the different flavors of physics education research through either REU programs, research opportunities as an undergraduate, and then into graduate school, I think sort of reading papers and going to talks and all of that stuff. That'd be where I'd start.
Thank you. Okay, so I've got one more question just for myself, so I don't take up any more of your time with this. So you mentioned that your focus is on university studies specifically. Is this something that you made as a conscious decision, or is it just kind of how things ended up with the research? And then a follow-up to that would be, do you expect some of this research to kind of trickle down to things like secondary education and even elementary education at that matter?
Yeah, great question. So why higher ed as opposed to K-12, for example? It was a conscious decision, and unfortunately, it's a very lazy explanation. So, studying K-12, the class sizes are smaller, the variability is huge. There's a lot of ethical sort of bureaucracy to get access to students at that level. It's really hard to do K-12 research, and doing higher ed is easy. And that's honestly sort of what we've done. So for folks, I think, to make it clear, I'm always in awe of folks who can do high quality studies at the K-12 level. It really is impressive that they can manage all of those pieces, because it's hard to do properly. And so certainly there's a lot of applications of our work that, a lot of implications, for our work at the K-12 level. And I, have done workshops with high school teachers, and I try to do that as much as possible to sort of reach out to folks to offer whatever I can, and to set up those lines of communication, even just with high school educators, because there's tons of implications for stuff that could be happening at those levels. And so, and high school, teacher preparation and things like that. So starting to get involved in that more and more sort of every year, but it's a work in progress for sure.
All right, thank you. Well, that's all the questions for me. I see Dr. Fultz, who is also a faculty member, he just kind of commented in and mentioned that we will reform out our Physics 1 lab soon. So
great. Happy to hear about it, and I look forward to hearing how it goes, and happy to help if I can provide any advice at any point.
all right, well, if nobody else in the chat has any more questions, or any of us here in the Zoom call, Dr. McBride, do you have anything that you want to say or ask?
I think that was a very informative talk, and I got my questions answered. So, well, why don't we give Natasha another round of thanks and applause there, and yeah, thanks again for taking time on your Friday to share with us your research in physics education.
Thank you so much for having me, and thank you everyone for coming.
All right, to all of those watching, we're going to be ending the stream here. So if you don't care to give a like to the stream if you're still watching, or subscribe to our YouTube channel, we would greatly benefit from that. But yeah, all right. Thank you, Dr. Holmes, and thank you to everybody that joined in. Okay, stream is ended.